Okay, Noah, I'm pretty excited to set up this average speed zone experiment.
Average speed zone? What is that?
Don't worry about it. I'll fill you in as we go. Now, let's take a look at my checklist and see if we're ready to get started. Is your seatbelt fastened?
Well, we're already driving, so yeah, my seatbelt is fastened.
Great. And are we driving in the slow lane?
Yeah, and we're going really slowly too.
But are we going exactly 37 miles an hour?
Hey, buddy, step on it, will ya?
Pete, I think we're upsetting the other drivers. Maybe I should
Don't
just...
sweat it, bro. We're here in the name of science. And besides, we're never going to see any of these people again.
I guess. Okay, and yep, we are going exactly 37 miles per hour.
Perfect. We're all set. I'll just start the timer. And the experiment is underway.
All right, what do I do now?
Well, let's check the chart. I got a lot of calculations here. It looks like we continue for about 30 seconds. And then, when you hear the timer beep, you need to speed up and move over.
Okay, but just to be clear, speed up by how much and move over how far?
I mean, you're the driver, but according to my chart, you should probably head over to the fast lane. Oh, there it is. Slam on the gas, dude. We gotta move.
Sorry.
Hey, watch it, man. You gotta be careful.
Well, I'm trying, but I'm totally speeding already. I'm going over 80. Can I just keep it here?
No, my calculation shows we gotta get up to 111. Step on it.
111? Why? Oh, great. This is just great. Your dumb little experiment is probably going to get me a ticket.
Howdy, gentlemen. Can I see your license and registration, please?
You know what? Let me handle this. Hello, officer. I'm Pete, and this is Noah. We're from the Math Club, and we're out here on official podcast business.
I'm sorry, officer. What my friend is trying to say is that he'd be happy to get the registration out of the glove box for you.
Dude, chill. I'm trying to get us a new listener here. Officer, do you like dad jokes and math puzzles?
Oh, dear Lord.
All right, you two. Out of the car.
This is the last time we're doing an experiment on the road.
Okay, but look on the bright side. My calculations were totally correct. We didn't even finish the experiment, and you still ended up getting a ticket.
Hey, everybody. Welcome to another episode of the Math Club. Pete, my friend, how are you?
I'm doing great, Noah. Glad to be here. Hey, Math Club, what is up? We're in the middle of summer, Noah. How are things going with you?
Pretty good. I mean, I know this doesn't sound like the funnest way to spend a summer, but I had cervical spine surgery about a month and a half ago where they actually had to go in through my throat and do some work on the vertebrae in my neck. Recovery has been really smooth, though. Listeners may have noticed my voice sounded a little scratchy in our last episode, but I think it's back to normal. How about you? What have you been up to this summer?
Well, I think I had a little more fun than spine surgery. Glad to hear you're doing better, though. I was lucky enough to spend 2 weeks with my family in Europe. We had a chance to visit the Netherlands, Belgium, France, and we even caught several days of the Tour de France while we were over there.
Wow, that sounds really cool. Did you happen to find any math while you were over there? I remember on your last trip to Europe, you came back with 3 Math Club episode topics ready to go. Did you find anything interesting this time?
Yeah, in fact, I had a kind of interesting math problem just sort of pop up during one of the car rides that I was in with my family.
Yeah, was it when you were trying to coerce your wife into driving 111 miles per hour to get her a ticket in Europe?
No, I would never do that to someone I care about. So we took a number of car trips, and on one particular trip, my 9-year-old Oliver decided he was going to play a game where we count the number of cars that we pass. Well, great. And so he started counting.
1, 2, 3.
But I said, Ollie, we could make this maybe a little more fun if we also subtract 1 every time a car passes us. So this way our total will go up and down and up, and it'd be kind of fun to see where we end up.
Oh, okay. Yeah, that does sound like fun. Kind of like a running tally.
Yeah, and now you'd be surprised. It was a little tricky to kind of remember, am I supposed to add or subtract? Those don't sound like tricky mathematical operations, but when you're on the freeway and you're paying attention to the landscape and you're having other conversation, it can be a little bit like, wait, is that -2 or -1? Where are we?
Right. And I am dying to hear how this translates into an episode topic.
Right. So we're driving along, playing this game, keeping track of the tally. Sometimes it's negative, sometimes it's positive.
3, 4. 3, 4, 5.
And at one point, the car navigation system makes some beeping noise. And my wife Emily said, I wish we were still using Waze. It warns you about things like speed traps and average speed zones, but Google Maps doesn't do that.
Okay, wait, there's that term average speed zone again, and I still don't know what that is.
Hold that thought, because we're definitely going to come back to it. At this point in the story, I just want you to note that Emily was concerned about accidentally getting a speeding ticket or some other traffic ticket. And so, she said, I wish we were using this other app. Well, at that point, Emily's mom, who was with us on the trip, Connie, says, I don't think there's anything to worry about. We're not going any faster than anybody else.
Okay, kind of an interesting thing for her to say when there's no real hard data.
Well, right, but I said, hey, Ollie, what is the current count on our tally?
I see where this is going.
Right, because he said,
We're at 13, Dad.
which means that actually we are driving faster than anybody else. In fact, 13 anybody else's.
I love it. I love it. What I love about this, Pete, is that any other time when Connie made that comment, there would be no way to either prove or disprove it. But the mathematician in the front seat just happened to go, wait a minute, we are running an experiment and we've got some information here.
It was really so funny because we're just playing a game. And what are the odds that an actual question about the traffic flow is related to the game that we're playing? I mean, it was just it was such a fun moment. So now I think it might be time to answer your question about average speed zones, because after all, that's what Emily was wondering about when she made the comment about the navigation system.
Okay, so I assume this is something they have over there in Europe that we don't have here. Or do we have it and we call it something else?
That's a good question. I don't think I've ever encountered an average speed zone here in the US. That doesn't mean we don't have them, obviously, but they're pretty common over in Europe, especially in the Netherlands, we noticed. So before I tell you what they are, let me ask you, do you have any guesses of what such a thing could be?
Well, just being put on the spot here without expecting it all of a sudden, I'm not sure. I guess my first guess would be it has something to do with taking all the different drivers' speeds and averaging them together. But I don't get how that might result in Emily thinking she's going to get a ticket. So I'm not sure.
Well, something is definitely being averaged, but it's not across different drivers. It's all within the context of each individual driver on the road. And so here's how average speed zones work. And here's why Emily was right to be potentially concerned about them in terms of getting tickets. At some point on the freeway, you will pass a camera, and that camera will take a picture of your vehicle.
Wait a minute, black and white, it would just capture the moment so nicely, wouldn't it? Oh.
Did you take the picture already?
Now, you pass the camera, you continue driving. At some point further down the highway, let's, just for the sake of example, say 10 miles later, a second camera takes a photo of your car. And so now the system has two moments in time where it knows your position at the beginning of the zone and at the end of the zone. And it knows that the zone is 10 miles long, and it knows how long it took you to get from the start to the finish.
I see. So in other words, it can compute what your average speed was while you were going through that zone.
Yeah, exactly. It takes the total distance traveled and divides it by your time. And that is, in fact, your average speed.
Okay, I understand that. But how does that lead to Emily may be getting a ticket. I mean, your speed can vary so much over a 10-mile strip. You might be speeding up and slowing down and speeding up again. All you're getting is an average speed. How is that going to help the police to determine if you were speeding?
Here is the interesting fact. Let's suppose that the freeway has a posted speed limit of 70 miles per hour. You've just driven through a 10-mile average speed zone, and suppose the system calculates your average speed at 72 miles an hour. Well, guess what? You've been speeding.
Oh, I think I get it. Because the only way for your average speed to be higher than the speed limit would be if at some point on that journey, your speed was higher than the speed limit. If your speed was always below or equal to the speed limit, your average couldn't end up being higher than that amount.
You're right. And in fact, there's a very famous mathematical result called the mean value theorem, which explains exactly why that must be the case.
All right. And that must be the topic you were inspired to talk about today.
Yeah, that's exactly right. Now, the mean value theorem is typically first encountered by students who take calculus, and this would be the first quarter of a typical year-long sequence in calculus, right around the time students are wrapping their head around derivatives. So this theorem has something to do with functions and derivatives, which in the context of our average speed zone example has to do with a distance function, namely how far has the car driven, and its derivative, which is simply the car's velocity.
Okay, now I want to remind you for a second, Pete, that I never took calculus. So there are some terms being thrown around here that I'm not too familiar with yet, namely derivative.
Yeah, so we can actually illustrate that pretty nicely in this example. Now, imagine that you are in this car, maybe with us cruising down a highway in the Netherlands, or maybe with your own family driving down to Orange County. You're sitting in a car, and as the driver, you're watching your speed, right? And how do you do that?
I keep my eye on the speedometer.
Exactly. And the speedometer tells you at the exact instant that you look at it, how fast you're going. That's not an average speed calculation. That's an instantaneous calculation, right?
Right. It's like a reading of how fast I'm going right now.
Right. And that's quite different from the calculation we would do in this average speed zone scenario, right? Like that's kind of a global question. On average, how fast were you going over this 10-mile stretch of highway versus the local situation, which is at this exact instant in time, how fast are you going? And this is an example of what a derivative is. It measures the instantaneous rate of change of a function.
Okay, but what if my speed isn't changing at that instant? Like, what if I have the cruise control set and my speed is constant?
I've got the old cruise control set at 35.
Then there is no instantaneous rate of change.
I see what's going on. So there are two quantities involved here. One is the speed at which you're traveling, which is what you just asked about. And the other, which I'm talking about, is the distance you've traveled since entering the speed zone. If you have your cruise control set at a fixed speed, say 72 miles per hour, then your speed isn't changing. Its instantaneous rate of change would be 0. Your distance, on the other hand, is definitely changing. And its rate of change would be
72 miles per hour?
72 miles per hour.
Okay, so a derivative is the current rate at which something we're measuring is changing. And in this example, since we're measuring distance traveled, that would mean the derivative is my car's current speed.
Right. Now, we've already mentioned your car's speedometer, but there's another readout on your dashboard that can help us out here. Any guess on what it is?
Well, if we're looking at how my distance is changing, it must be the odometer, right?
Bam! Your odometer will keep track of the distance you've traveled. And if we set it to 0 at the exact moment we enter the speed zone, then it quite literally represents our distance function.
Just like how the speedometer represents our speed function.
Yeah, and if we look at them together, we have a really nice way to conceptualize both a function and its derivative. The odometer is the function, and the speedometer is the derivative.
Now I get it. Since the odometer is the function in this scenario, that's the change we're measuring as time goes by.
Exactly. And remember, we're not even really ever measuring your speed at any instant in this example. We're only recording the time when you entered the speed zone and the time when you left it.
You know, I hadn't thought of that, but We're getting my average speed through this zone without ever once measuring or recording what my speed is.
That's right.
And for that matter, we're never really checking what my distance is either. We know that the total length of the speed zone is 10 miles, but the only variable we're measuring here is time, the time it takes me to go those 10 miles.
And that's what makes this an interesting process. We're inferring information about your speed without ever measuring it directly.
Yeah. So instead of setting up radar guns every quarter mile or so along the freeway, they can calculate my average speed through the whole zone with just 2 cameras and a clock. And if my average is above the speed limit, I'm hosed.
Right. Now, let's get back to the mean value theorem, which really is the reason you'd be hosed if your average speed were above the speed limit. The theorem tells us that if we look at your average speed across the zone, then there's some moment in time, at least one instant, when your instantaneous speed must be equal to that average speed.
So what that means is that if we determine at the end of this that my average speed was 72 miles per hour, then there was some point along that journey when I was going exactly 72 miles per hour, even if it was only for the briefest of instants.
Yeah, that's right. If you had, say, a video recording of your speedometer over that entire 10-mile drive, you would see at least one moment when the speedometer said exactly 72 miles per hour.
And that's why I would get a ticket. We've just concluded that I must have been going 72 miles per hour at some point, but the speed limit's only 70. That's really cool. But how exactly does it work? We just said that we never measured my speed, and yet we're able to say I must have been speeding at some moment. How is that possible?
Yeah, totally interesting question. And it goes straight to the heart of the mean value theorem and what makes it actually true. And I think we can explain it by looking at a related but simpler stripped down example. So let's get out of the car and head out to the backyard because I have a baseball and a stopwatch that we can use to set things up.
Okay.
What I'd like you to do, Noah, is to take that ball, toss it straight up into the air, and then when it comes back down, go ahead and catch it. And I will time how long it's in the air for.
All right, here we go. Tossing and catching.
So the ball was in the air for 4 seconds, and let's assume that you tossed the ball up at, say, a height of 5 feet. And it just so happens that you catch it again when it comes back down at a height of 5 feet, so that it starts and ends at the same height, 5 feet above the ground.
Okay, sure.
So now that you've tossed the ball up and caught it again, here's my question for you. What was the ball's average vertical velocity over the course of those 4 seconds?
The average vertical velocity. All right, well, it had a positive vertical velocity as it went up, right? And then it had a negative vertical velocity when it came back down. So those are going to sort of cancel each other out when we average them together, right?
Right.
The ball started at a height of 5 feet off the ground. 4 seconds later, it ended at a height of 5 feet off the ground. So it seems like over the course of the throw, it had a net change of 0. So isn't the average rate of change just 0?
Yeah, the average velocity was 0 because, after all, if I take the final height of 5 and subtract it from the initial height of 5, I get 0. It appears to have moved 0 feet over the course of 4 seconds. So the average velocity is 0.
Okay, but Pete, wouldn't that then mean that the mean value theorem would imply that somewhere along that route, the actual velocity matched the average velocity? Wouldn't that mean somewhere on the route, the ball actually had a vertical velocity of 0?
Aha!
Oh, it absolutely means that.
Oh, bugger!
And I'd be willing to bet you can tell me the exact location of the ball when it had a velocity of 0.
I can tell you the exact location. Oh, wait a second. I get it right in the middle, right? When it was like 15 feet in the air and it stopped going up and started coming down, there was an instant there where its vertical velocity was exactly 0.
Right. Now, let's imagine the movement of the ball as a function. To do this, we can measure time on the horizontal axis and the height of the ball on the vertical axis. So at time 0, when you release the ball, it's at a height of 5 feet. And that means that the starting point of the graph of our function would have coordinates 0, 5.
Okay, so then does that mean that the ending point of our graph would be 4, 5? Because after 4 seconds, it was at a height of 5 feet again?
Yeah, that's right. But let me ask you a slightly trickier question. What do you think the coordinates would be when the ball hits its maximum height?
Its maximum height. So that's after just 2 seconds when the ball's 15 feet up. So that point would be at 215.
Yeah, nice. And if we were to draw all of the points in on this graph, what we'd end up with is a really nice upside down parabola. And the vertex of that parabola would be right there at that point you found, 2, 15. Does that make sense? Can you picture this?
Yeah, got it.
Okay, great. Now, I want you to imagine drawing a line between the starting and ending points of the graph. Both of these points have a height of 5. So what will that line look like?
It would be like totally flat, horizontal, just straight across.
Yeah, and in fact, that line will have a slope of 0. So that slope is a measurement of the average rate of change over the entire graph.
Okay, that makes sense.
Now, let's look at that maximum point on the graph again. And what if we draw a tangent line right through it? What would that line look like?
Okay, so a tangent line has to touch the graph at a single point without crossing it. So wouldn't it also have to be flat and horizontal, kind of like a perfectly balanced teeter-totter perched right at the top of this curve?
Yeah. In fact, that's actually a really nice visual, that teeter-totter sitting up there. That line has a slope of 0.
Okay, but why do we care about the slope of the tangent line?
Because in a graph like this, to find the instantaneous rate of change at any particular point, the way you do it is you draw a tangent line through that point and you calculate its slope. Whatever the slope of that tangent line is, that's the instantaneous rate of change, what we also call the derivative.
Oh, okay, I think I get it. And in this case, the slope is 0 because at that exact instant, the ball isn't going up or down. It's that moment in between when its vertical velocity is 0.
That's right.
So like you said, this function has a maximum value. And at that point, the rate of change is 0. It's flat. It's just like the average rate of change over the entire curve.
Totally. Now, here's what's interesting. We figured this out by looking at the graph and making some observations about its shape. And we found a tangent line whose slope is equal to the average rate of change for the function. This is exactly what the mean value theorem predicts, that we'd be able to find that horizontal tangent line. You know, it's kind of like the theorem knew all along that that line was going to be there and that we'd be able to find it. But here's what's really cool. With this example, we have basically just given a proof of the mean value theorem for functions whose starting and ending points have the same exact height.
Okay, and I understand that, but what if the starting and ending points don't have the same height? Like in the average speed zone example, the car doesn't start and end in the same place, so we wouldn't get a flat slope for the average rate of change. Let's change things up and do a baseball example that's more like the average speed zone. Let's say, just like before, I throw the ball into the air from a height of 5 feet, goes up to 15 feet, and then it turns around and starts coming back down. But this time, you're standing there on a ladder and you catch it before it has a chance to come all the way back down. Let's say 3 seconds in when it's still 11 feet off the ground. What happens to our graph now?
Now that's $1 million question.
Here it is for $1 million. Let's play.
In this case, our starting point is still at 0.5, but our new ending point, which shows that I caught the ball 3 seconds later at a height of 11 feet, that point is now 311. And if I connect those 2 points with a line, I get a slope of 2.
And the reason it has a slope of 2 is because to connect those 2 points, we'd have to move up 6 and over 3. So it isn't a horizontal line anymore.
Right. Definitely not horizontal. definitely doesn't have a slope equal to 0. And that means the mean value theorem predicts that there must be a point on the graph of the parabola somewhere where the tangent line also has a slope equal to 2.
And is that going to be at some random point, or will that be at the curve's maximum height again?
Well, it definitely won't be at the maximum height this time, but I think you already know why it won't be.
Oh, okay, of course, because at that maximum peak, when the ball stops going up and starts going down, its vertical velocity right there is 0. That teeter-totter tangent line at the peak still has to be flat with 0 slope. So this tangent we're looking for with a slope of 2, it's not going to be the one right up there at the maximum peak.
Well, not yet anyway.
What does that mean? Not yet.
Another $1 million question.
You realize you owe me $2 million now, right? I can take cash, check, Venmo, or PayPal.
Oh, I've got a check for you, all right, and it is definitely in the mail. So what do I mean by not yet? Well, what I mean is this. First, we need to perform a little trick, a sleight of algebra, if you will.
No, I will not.
All right, moving on. So what we want to do is transform this new scenario so that it's just like the previous one. What we need is some way to equalize the heights of the starting and ending points. Can you picture, I don't know, something that we could do that might make this happen to the graph?
Okay, so we've got one point at a height of 5, and the other is higher up at a height of 11. So what if we rotate the whole graph clockwise a little bit so that the two endpoints end up at the same height?
Hey, that's a really good intuition, actually. And it's almost right. Technically, what I have in mind is we're going to subtract a linear term from the original function to change it. But honestly, for the sake of illustration, let's stick with your rotation idea because it basically gets it right.
Wait a second, because while you were talking, I think I just pictured something cool here. And I think I see now why you said this tangent we're looking for isn't at the maximum peak yet. It's because when we rotate the whole graph like this, it's going to become the new maximum point, isn't it?
Exactly. You got it.
Nice. So we've rotated this whole graph so that the two endpoints now define a flat horizontal line with a slope of 0, like the last example. And after this rotation, the point that ended up as the new maximum peak will have its own flat teeter-totter tangent line passing through it at the top, again, just like in the last example.
Well, I think you really did picture something cool because this is pretty much exactly right. So here's a question. If we rotate this graph and these two lines all together back to the original starting point, what do we end up with?
Well, since these two lines are rotating back together, kind of in lockstep with each other, the tangent slope is going to stay exactly in sync with the slope of the other line. It's going to match it. It's going to have a slope of 2.
Right. See, the average rate of change is 2. And now we've proven that there is indeed a point on that curve where the tangent slope, that instantaneous rate of change, it's also equal to 2. It has the same value.
Wow, that really is cool. And now that we understand that, let's wrap it all up by explicitly tying this all together with the average speed zone example and saying how this all works.
Yeah, so like you asked a couple of minutes ago about the baseball where the starting and ending heights are different, that's really very similar to the average speed zone example with the car, because when it enters the speed zone, its total distance traveled in the zone is 0 miles. And when it exits, its total distance traveled is 10 miles, because that's how long the zone is.
So our graph of this one would have one endpoint at 0, 0, and one, well, that's up at 10, but how far over it goes would depend on how long it takes you to go through the speed zone.
Yeah, exactly, right? It just depends on the particular car. But the point is, all three of these examples have a single abstraction in common. Namely, they're each modeled by a continuous function, and that function is defined over a specified interval, and every point on the graph of this function has a tangent line. So we would say that it's differentiable at every point. If that's true, regardless of the function, the mean value theorem will tell us this result that there is some instant when the tangent slope is equal to the average rate of change.
That makes complete sense. And I just had an interesting insight while I was picturing it just now while you were talking. In the average speed zone example, we don't even have the graph of the curve itself. We only have the graph of the line between the two endpoints. And that's all we need to know that at some point along that path, there's another spot that had that same rate of change.
Exactly. And this is the beauty and the power of mathematics. As long as the hypotheses are satisfied, namely you have a continuous function that has a derivative at every point, the result applies. It doesn't matter if you can picture the example or not. You don't have to have a graph in front of you. You just need to know a few properties, in this case, two properties about the function, and bam, you've got this result.
Okay, this is all very cool. It's really clicking in and making sense. And I totally understand the theorem now and how the police in the Netherlands can confidently know that I was speeding if my average rate of change was above the speed limit.
Well, the police that have taken calculus can do that. Everybody else is back at the station working a desk job.
Working a desk job. You know, this all reminds me of a puzzle I heard once. Why don't we use it as a challenge? How about I tell you the puzzle and we challenge our listeners to see who can be the first to contact us with the correct answer? How does that sound?
I think it sounds a little mean.
I see what you did there.
Sorry for the dad joke. I think that's a great idea. Let's do it.
All right, so here's the puzzle. Let's assume that I am about to make a 60-mile round trip between Livermore, where I live, and Oakland, which is 30 miles away. Going from Livermore to Oakland, I drive an average of 30 miles per hour. But I want the average speed of my entire round trip to be 60 miles per hour. So the question is, how fast do I have to drive on the return trip from Oakland back to Livermore to get an overall average speed of 60 miles per hour for the entire trip?
Oh, I like that. And it's not so mean after all. I think that's a good problem for our listeners to think about.
Yeah, so how about we give a shout out on our next show to the first listener to contact us with the correct answer? Pete, why don't you remind everyone how they can reach out to us if they want to share their answer to the puzzle?
Sure, there are several ways for you to get in touch with us. Our favorite is for you to leave a voice message for us at our SpeakPipe page. The URL is speakpipe.com/mathclubpodcast. You can also write into us on our Twitter page. Our handle is @mathclubpodcast. And finally, the old-fashioned way.
People might just need a little old-fashioned.
You can send us an email. Our email address is mathclubpodcast@gmail.com.
That's right. And all of that reminds me, Math Club, that we are also still collecting your stories about your favorite numbers for our upcoming episode, My Favorite Number. So if you have a favorite number, we would love to hear about it. You could contact us in any of those ways Pete just mentioned and let us know what your favorite number is and why. And who knows, you just might hear yourself on our future episode.
Oh, wouldn't that be cool? I like that. All right, Math Club. Well, we will keep an eye out for your incoming messages. And until then, we'll see ya.
I better get going because I have quite the drive home. And if I don't leave soon, my average speed is going to get me another ticket.
Bye, Math Club.
See you next time.